All right, so this is a hyperbola. You kind of remember, um, what, that was like 2 weeks ago? It was only a week ago. A week ago, we watched that video of the two cones and we sliced through the cones, right? So yesterday, we looked at ellipses. Last week, we looked at parabolas. If you slice through that double cone through both the top and the bottom base of the cones, you get a hyperbola. Basically, it kind of looks like two parabola-ish shapes that are opening away from each other. Okay? Now, with each conic section, we have discussed a geometric property. A hyperbola is the set of all points in a plane the difference of whose distances from two distinct points is a positive constant. So before you write this down, just take a break. The only difference between this definition and the ellipse definition is this word right here. Yesterday it was sum, today it's difference. Go ahead. You can see that we still have a center. We still have two vertex points. We also have two foci, but notice how the foci are further away from the center than the vertices. Okay, that's different. This is a horizontal, and we'll get into the difference between horizontal and vertical here soon, but this is a horizontal hyperbola because the curves are opening horizontally and the foci are horizontal from each other and the vertices are horizontal from each other. Okay? One fun thing that we have are these two asymptotes which give the hyperbola that shape. Okay? What we'll do is we'll plot the asymptotes, we'll plot the vertex, and then that'll be how we decide how wide our hyperbola is. Okay, we won't have to get another point. Now, we're going to call this the transverse axis. It's the line that passes through the foci and the vertices in the center. Okay, kind of like a parabola has an axis of symmetry. All right, this is kind of along those same lines, but we're talking about a hyperbola. This is the transverse axis. Okay, and since it's horizontal, we have a horizontal hyperbola. Okay, now I'm handing out, you have a hyperbola in front of you and you have a ruler. What I would like you to do is make a point anywhere on the hyperbola. So let's say I pick this point right here. Actually, draw it. What I want you to do is I want you to measure the distance to each foci, and I want you to calculate the difference. So make two measurements, write them down, and then subtract the two numbers. You'll probably want to use centimeters. And find those two distances and subtract them. Now I want you to make another point and do the same thing. Remember, you are measuring pretty small distances. But what should happen is those two differences should be pretty close to the same number. Still got the same thing? Yes. Yes, we should. There's a little bit of room for error because we're trying to measure, right, with a ruler. But we all should be getting roughly the same thing. Basically what we've done is we've demonstrated that geometric property of a hyperbola. We could do this all day. You could take any point on that hyperbola, whichever side of the curve, it doesn't matter, and when you take the distance to the foci and subtract them, you should get the same number throughout the entire hyperbola. Now, before we go to lunch, let's go ahead and write down all of the boring stuff. All right? Here is the standard form of a horizontal hyperbola? What is the only difference between standard form of a hyperbola and ellipse? The subtraction. Okay, there's subtraction between the x squared and y squared instead of addition. That is how you're going to tell the difference between an ellipse and a hyperbola. Our center is the same. One thing that is different is c. C squared is a squared plus b squared for a hyperbola. Okay, so that is different. Notice on my picture here that the vertex is still A away from the center, and the foci are both still C away from the center. Okay, so that does not change from hyperbola to ellipse. The vertices are still A away, and the foci are still C away. Now, you don't see anything in my picture about B. We're still going to use B like we would in an ellipse, but instead of making a shape, we're actually going to use B to help us with those asymptotes. Okay. All right. What is going to be different about a vertical hyperbola? The y needs to be positive and the x is the one that's being subtracted. Okay. With a hyperbola, it doesn't matter if A is bigger than B. A is just always going to be with the positive squared term. Okay, so A will always come first. It does not matter which denominator is bigger. So our center is still HK. We're still going to use A to tell us how far our vertices are. We're still going to use C to tell us how far our foci are. But then you see in this picture, okay, we need to make asymptotes, all right? So what we're going to do, and I'll show you in our two examples, but we are actually going to plot point B away from our center, and then we're going to create like this invisible box. And our asymptotes will go through the diagonals of that box. So basically, we're still going to plot A and B like we would in an ellipse, but instead of an ellipse, we're going to make an invisible rectangle so that we can draw in our asymptotes. Okay. It's not something, some of you will not draw it at all. Some of us, if we need to draw it, we'll draw little dotted lines that are really, really light. But we're going to use that rectangle to get our asymptotes. Now there is something that we need to review back from algebra before we move forward with these. You guys are all pretty good at writing the equation of a line. But typically what you do, if I give you a point and if I give you slope, you write y equals mx plus b, you plug in your coordinate x, y, and you solve for b, and then you give me a y-intercept form line. That is too much work for us anymore. You are at the end of your pre-calculus time, and a lot of you are about to move into calculus. And I will tell you that the lines that we write in calculus, we leave in point slope form. We don't even like solve for y. So we're going to start practicing that starting today. Point slope form, do you remember it? Well, it's y minus y1 equals one more piece. So if I said that our slope was 2/3 and it went through the coordinate 1, 2, then we would write the line y minus 2 equals 2/3 times x minus 1. Maybe back in algebra you would distribute the 2/3 and then add the 2 over. We are literally going to leave it like this. You are not going to solve it out. You're going to leave it like this. I know it's not a simplified line, but I don't really care. All right? Because what's going to happen is we're going to use our center to give us that coordinate, and we're going to use A and B to figure out our slope, and then we're just going to leave it. So when we get back from lunch, we are going to go through 2 examples of a hyperbola, one that opens horizontally, one that opens vertically, so we can see the differences. And we'll work on some more algebra skills because one will definitely be where we have to compute this with. Enjoy your lunch. Please write down this equation. To your neighbor and tell them which direction you think this hyperbola opens. Turn to your neighbor again. All right, pod 4, what do you think back there? Oh, pod 3, Amy. Horizontal, and we know that because? Okay, the x squared is the positive 1, so this is going to be a horizontal hyperbola. Great. Let's talk first about the center. Jackson, where's the center?
0,
0,
0.
0. Do you agree with Jackson?
Yes.
Okay. All right, here's where it gets our A value. Finn, what would it be?
It would be 3.
Okay, A is 3. A is always associated with the positive square term. All right. You can also think of it as, since 9 is underneath the x, we're going to move horizontally 3. So our vertices are at 3, 0, and negative 3, 0. Okay. Now, we don't have minor vertices like we do on an ellipse, but B is still important. What is our B value? Our B value is 5. So what we are actually going to do is we are still going to plot a couple of invisible points 5 units away. And then when I draw in green, it means I'm drawing something very, very, very lightly. Okay, I just can't like put less pressure on a marker, right? So with these 4 coordinates, we are going to create a rectangle, an invisible rectangle. This is not actually a part of our graph. It's kind of like the frame in the framing method where we drew it to help us, but it really wasn't a part of the graph. Okay? And then what happens is our asymptotes go through the center and the corner. So they become the diagonals of this rectangle. So through the center and corners, we're going to draw our asymptotes. From here, we are going to look at the picture to determine what our slope is. Okay? What is the point that both of these lines go through? 0, 0, which is the center, okay? So the center is going to be the point that we use for our point slope form. What is the slope of this line right here? Up 5/3, right? So we have a slope of 5/3. So we would have the line y minus 0 equals 5/3 times x minus 0. Which we can simplify, right? Typically, I won't have you simplify, but zeros just look silly. So we'll rewrite it. Okay, what is the slope of this line right here? Negative 5/3. We go up 5 and left 3. That's going to happen every time where both lines are going to have just opposite slopes. So what you can do, instead of writing 2 different equations, you can just say plus or minus on your slope and just write 2 equations in one. Now, as far as the shape of your hyperbola is concerned, you're going to take your vertex and you are just going to draw your U shape so that it approaches the asymptotes. Okay? The asymptotes give you how wide to make your hyperbola. So just approach those asymptotes. One more task. What are we missing? Okay. We need the foci. Amanda, what did I have you write down for the equation for C? Okay, this time for a hyperbola, C squared is A squared plus B squared. A squared is 9 and B squared is 25. So C becomes the square root of 34. Square root of 34 is almost what integer? It would be almost 6. Okay, the square root of 34 is close to the square root of 36, which is 6. So we will move from the center 1, 2, 3, 4, 5, almost 6. 1, 2, 3, 4, 5, almost 6. And those are our foci. Since we moved horizontally, okay, our x coordinate changed. So what we can write, we went from 0 and we added radical 34 and stayed at the same height. And we took 0 and we subtracted radical 34 and moved to the left radical 34 and stayed at the same height. Sure makes it nice when the center is the origin. Question. A lot of similarities between hyperbolas and ellipses, which is why we're doing them back to back. All right. All right, we have one more example, and then we'll be done. Maybe even in time for you to start your homework. Okay, you're writing down this general equation. How do we know that it is a hyperbola? Okay, so first of all, we have x squared and y squared. Second of all, one's positive, one's negative. Okay, and since x squared and y squared have opposite signs, we know it's going to be a hyperbola. Which one is the positive one? Y. Now, I don't know if that's necessarily going to mean, depending on what happens with completing the square, that doesn't officially tell us that this is going to be a vertical hyperbola, but chances are good. Okay? All right, so we're going to need to complete the square just like we did yesterday with our ellipses. So we're going to take a similar strategy. We need to group the y's together and then the x's together, and that 47 needs to be on the other side. Okay. I like to keep the square or the positive term first, so I'm going to keep y squared first and then x squared second. All right, since y squared has a coefficient of 16, we will factor out a 16 from our y terms. That means we're left with y squared plus what? 4y plus a mystery number. We'll come back to that later. Technically, what is the coefficient of x squared? -1. Okay, this is where the algebra part gets a little tricky. With the hyperbola, we're always going to have to factor out a negative coefficient. So we have to factor out -1, which means left over is x squared minus 2x. All right, Molly, what completes our square for the y? 4. 4. Are we really adding 4? 64. We're really adding 4 times 16, 64. Okay. Hannah, what completes the square here? 1. Are we adding 1? Okay, we're adding 1 times this -1. And this is where people run into trouble. It is very easy to forget that we're multiplying by this negative number. So what we're really adding is -1. So that's what we need to add to the other side to balance our equation. So what we have is 16 times y plus 2, the quantity squared, minus 1 times x minus 1, the quantity squared, equals 68. just like with an ellipse standard form equation, we need this to be set equal to 1. And so since there's a 16 on the other side, we'll go ahead and divide by 16. Now, you wouldn't necessarily need to write this y plus 2 squared over 1, but I like to do it just so I can emphasize that that is what my a squared term is. Okay, so our assumption was right. This is going to be a vertical hyperbola. We know that because the y squared is the positive 1. Yeah.
So like it could be different if you ended up with like a negative on the other side of the equal sign, so then you divide it over and swap them.
Yes. Yeah. Did you hear that question? Okay. It is possible that this would have been negative, and so then when you divided by that number, it would switch the positive and negative. And that's why I said we can't be 100% certain that this is ortho. Okay. All right. Let's identify everything that we need to graph here. Our center, Nicole, where is it? Negative 2, 1. I like the negative 2, and I like the 1. I like the positive 1, and I like the negative 2. Nicole, you're looking at the right numbers. And I'm glad you made that mistake, okay? This is so easy to do, especially with hyperbolas. When we have a vertical hyperbola, it's really easy to just grab this number, right? But they're out of order. The y comes first because it's vertical. But we still need to make sure we grab the number with the x for the x coordinate and the number with the y for the y coordinate. Okay. Our denominator is 1 underneath of the positive term, which means a is what? A is what? Kind of boring. So, since it's vertical, we will move up 1 and down 1 for our vertices. Oh, those are not good. I know. What is our b value? Our b value is 4. Okay. Since our b is associated with x, the horizontal variable, we're going to move horizontally 4, and we're going to plot invisible little coordinates so we can create our invisible rectangle. With your invisible rectangle, go ahead and draw your asymptotes. Whoa, got a little crazy there. Through the diagonals. Now you have like straight edges that are within reach, I collected your rulers, but you have like IDs and stuff that you can use. I don't really have that up here, so sorry about my asymptotes. Okay. Now we can create the shape. So vertically opening, go ahead and draw your curves. Let's write the equation of those asymptotes. Okay. Remember point slope 4. Since both lines go through the center, I want you to use the center as your point. So our center is 1, 2. So that's the point that you're going to use. The positive slope line, what does it slope? Up 1/4, right? The other line has a slope of -1/4. So we can just write two equations in one. Our slope is positive 1/4 and -1/4, and they both go through the center. Okay? Now, some of you may be wondering, like, how do I remember the slope? Okay? You're going to have to look at the picture. Because when we have a hyperbola that opens horizontally, our slope is b/a. When we have a hyperbola that opens vertically, we have slope that is a/b. Okay? I don't want you to remember a/b versus b/a. I want you to think about what the picture looks like and use the picture to write the equations of your lines. Okay, did you have a question? Raise your mind. Okay, last but not least, let's get some foci on there. So we know c squared is a squared plus b squared. A squared is 1 and b squared is 16. So we know c is radical 17. Radical 16 is 4, so we know radical 17 has to be just over 4. So from the center, count the same direction as your hyperbola, so in this case vertically. 1, 2, 3, a little bit more than 4. And then 1, 2, 3, 4, a little bit more. Since our C value is irrational, remember I will allow you to write both coordinates in 1. We moved vertically, so we kept an X value of 1, but from -2 we went up radical 17 and down radical 17. So we can write that as -2 plus or minus radical 17. The hyperbolas. What do you think? It's the same. Identifying A and B. You gotta plot A and B. We're just kind of creating a different shape out of it. Okay. The biggest piece you're gonna have to remember is the asymptotes, and like I said, draw the picture and then read the graph to get your slope. Okay. Don't try to remember A, B, B, A, any of that. Okay. All right. Your homework assignment is on your gold sheet. It is important that you do your homework, at least the required ones. You'll want to practice graphing, and you'll really want to practice the algebra ones, putting them into standard form. Okay, the hyperbola ones are probably the ones that get goofed up the most because of that negative sign. Okay, our quiz is on Wednesday.